models were.
So pick up me?
Yeah.
Okay, great. Yeah. So with that in mind, actually, I think this is sort of leads into this first question here, which is seems to be on a lot of people's minds, which is this sort of insecurity that maybe we're kind of done. Like we've solved these problems, and the answer is actually really boring. You just need to collect a lot of money and then use the money to collect a lot of data and buy a lot of GPUs and crank the optimizer, pay the electricity bill. And I'd like to make the case today that we're nowhere near to that, and that actually scale in some ways has taken one question off the table, which is how to get a state-of-the-art top accuracy result on a data set. But there's all sorts of questions that are orthogonal to these scale questions that are really interesting and fundamental to these models. So in particular, one aspect of this problem is control. How do you steer the model and get it to produce output that matches what you've asked for? And again, I think there's sort of a perspective that says, text is all you need. You know, I'll just prompt the model, I'll tell it what I want. And I will say to that even in the vision domain, where these text prompted vision models have become very successful, you talk with artists, and there's a lot of frustration about the limitations of these models. If you want to get it, like, I have an image in mind of, like, I want this texture. Maybe I even have an example of the texture that I want the model to produce, and just trying to describe in words this texture that you want the model to generate is almost impossible. It's very good at these sort of like structural components and seeing composition, but very bad at some of these more low-level details and particulars. Another issue that I see with the current toolbox is our ability to generalize these methods to diverse modalities. So I've spent a lot of time working in this music domain, and it's immensely frustrating to read these papers in vision or NLP, and they're very grandiose in their claims of the generality of their learning tools. Some new data domain, and it doesn't work at all. And working in a broader base of modalities, I think, is an important regularizer for our community to understand the challenges that are fundamental to learning, and to not get too self-congratulatory about how good our NLP toolbox has become. And finally, another set of questions that are completely orthogonal to these scale questions are these issues of governance. So we saw recently, as ChatGPT got popular, some communities online moved to try to ban the use of these products on their platform. But there's really no way to enforce these bans. In fact, like, the whole point of these generative models is that they're very convincing in their outputs. So you're trying to ban ChatGPT, but ChatGPT is trying to fool you into thinking that it's a human. How are you supposed to moderate and enforce this ban? And all these questions are completely orthogonal. Like, you can't solve any of these problems by scaling the model up. So there's a lot of work still to be done. And particularly in the music domain, I'm going to focus on two of these questions today. And in the music domain, there's this sort of observation that people have had about music, that writing about music is like dancing about architecture. It's really hard to describe in words what you want, or what's going on in music composition. And it's hard to describe what's happening in a music composition. It's also hard to prompt the model to produce the music that you want it to produce. And so there's a fairly open-ended control question here in the music domain about how do we steer these models? How do we want to steer these models? I actually think a lot of the interesting questions that will emerge over the next few years in the music space and in other spaces as our sort of core modeling toolbox becomes more mature is HCI questions and interface questions, and how do we design models that are really promptable and controllable and responsive to the needs of our users. And also sort of looking to this domain that's a little bit off the beaten path, we'll basically see when we start to look at domains like music that a lot of the components of our modeling toolbox break. So one challenge that I've been talking about a lot for years, that's extremely obvious in the music domain, that was not obvious until very recently in text, is that we should care about long context. So now today in 2023, everyone will acknowledge that, okay, long context is important. We all want our models to have longer context. And this has happened because we realized, we want to do in-context learning. We want to be able to stuff an entire data set into the prompt of our language model. And suddenly I want to be able to condition on 100,000 tokens. And how do I do that? But 5 years ago, when I talked to people in NLP and I said, I want a model that can look at 10,000 tokens, they said, who cares? Like, no document on the internet is longer than 1,000 tokens. Why should I care about one context? And it's just one example of how looking at different modalities can highlight different aspects of the learning problem that may not be apparent if we sort of stick to the beaten path. So then sort of a third component of my work that I won't talk about too much today is these governance questions that are becoming increasingly important as these models become used in society, and we want to be able to write regulations about them. We want to be able to moderate content that's produced by them. So I have work on watermarking that I've thought about. How could you provide a tool to say Stack Overflow if they wanted to be able to moderate their platform and police generated content on their platform? There's also questions of copyright and attribution that I won't go into today, but are extremely relevant in the music domain where copyright is extremely strong compared to text. So because of just sort of the quirks of how the law works, companies like OpenAI have been able to get away with a lot of scraping that might be a much more tricky proposition if you're working with data in a domain like music where content is policed much more. And then there's all sorts of other questions like privacy. They, again, are like completely orthogonal to how big a model can I train with the resources that I have. So with that in mind, today I'll be talking about music. And in particular, there will be two parts of this talk. The first part where I'll be sort of focusing on some unique challenges that are rising in this music modeling domain, in particular, how we can apply control to temporal point processes of the music as an example. And by control, you should really think about this as conditional probability distributional estimation. I want to be able to estimate a conditional distribution over music given some control inputs that I'm going to use to guide that generation. And then after building up this sort of technical framework for applying control to these to models using this idea called anticipation that we'll introduce, I'll apply it to actually run this model on some music and train up some, I'll call them, well, I'd been calling them medium scale language models, although realistically today they're quite small, but working within the context of the methodology and tools of this large language modeling regime, and looking at what happens when we point some of this modeling toolbox at the music domain, layering this idea of anticipation on top of the modeling toolbox in order to get some controllability. And this is joint work with several collaborators, David Hall and Percy Lang at Stanford, and Chris Donahue, who I overlapped with at Stanford, but has been at Google DeepMind for most of the duration of this work. Okay, so let's talk about this modeling idea called anticipation. And as a motivating example, I'll give you this example of music. So let's suppose that we have some musical melody that I'll illustrate sort of visually as this sequence of blue dots that are intended to represent notes. So the y-axis of these dots is going to be the pitch of the note, and then time is on the x-axis. And you can think of this as like a visual rendition of a melody that's evolving over time. And I'll call this melody the controls. So these are going to be the inputs to my model. What I'm interested in doing is generating a harmonizing accompaniment to this melody. So a whole bunch of other notes situated in time, correlated with these notes in the melody, that I'll call the events. And I'm interested in this conditional density estimation problem of building an estimator of the probability of this sequence of events, E1 to N, given these controls U1 to K. So this is my controllable generation task. And as a warm-up to this task, I'm going to make some simplifying assumptions that will then relax later and think about the full problem. But in particular, what I'm going to assume is that I have a one-to-one correspondence between these events and these controls. So I have N events and N controls, and this is going to make life easier in ways that won't work in general, but will help us understand the ideas. So how could I go about building this conditional model? Well, sort of the oldest trick in the book, and Ilya Sasiever and folks were building these models in 2014. They called them sequence-to-sequence models. I'm sure people were doing this before Ilya, but this is kind of the origin of this, at least in the modern context, is to say, well, okay, take these controls, construct an artificial sequence where you put the controls in the first half of the sequence and the events in the second half of the sequence, and then train an autoregressive model to predict the sequence of tokens. And if you want to condition on the controls, just prompt the model with the sequence of controls and then run the autoregressive model from the end of the control sequence to generate the events. This is a totally reasonable way to solve this problem. Until I have 10,000 events. Okay. So now let's suppose I have 10,000 events. Well, maybe I'm modeling this. Now I need to think about how I'm modeling this sequence. So if it really is an autoregressive modeling, conditioning on everything in the past, maybe I'm. But if I'm using like an LSTM or RNN, well, these models aren't good at holding on to long context. So maybe it's forgotten about the controls at the beginning of the sequence by the time I'm starting to generate event one. But maybe like event one is supposed to be like coupled with control one, like these are supposed to be occurring at the same time. So U1 is actually the most important control for predicting event one, but I've lost it in the history of this sequence. And with more modern like transformer models that have explicit context windows, it might not just be that it's hard to look back all the way to U1. It might be that it's actually not in the context window of my transformer. And now I'm just dead. Like I need to generate U1. I need to know what U1 is, but U1's so far back in the sequence that I have no idea where it is. So that's no good. The saving grace here is that this is an artificial problem. I decided to set up my problem this way by appending the controls to the event. So maybe there's some other way that I could arrange the learning problem to make this a little bit easier. So one thing I could try to do, well, what if I like interleave these two sequences? So now I said that U1 is the most important control for predicting E1. So let's take that hypothesis seriously and then just put U1 right before U1 and U2 right before U2. And that's fine and great. But now this sort of sucks because I have all of these U's up front, like this is my conditioning signal. But when I'm predicting E1, I'm not using all of them to make that prediction. I'm only using U1. And E2 only sees U1 and U2. So this sort of sucks too. This is not a great solution. So interpolating a little bit between these two regimes, what if I just do this interleaving thing, but with an offset? So now, instead of pairing off U1 with U1, U2 with E2, et cetera, I pair off U3 with E1, U4 with E2, and put the early controls at the beginning of the sequence. And now I kind of have a little bit of a knob here that I can tune. And I could maybe set delta equals 4 and have a prefix of more controls to get a running start on this conditioning problem. And actually, if I set delta equals infinity, then all my controls get shifted to the beginning of the sequence, and I recover this sequence-to-sequence modeling problem. But now I have a knob I can control. And by picking this, I get to pick sort of how long range these artificial conditional dependencies are in the sequence versus how much I'm conditioning on when I'm predicting each event in the sequence. So we can formalize this a little bit, and I can say like exactly what I'm doing when I arrange my sequences this way. But basically what I'm doing is, if I have an autoregressive model over sequences that have been constructed in this way, is I'm making a conditional independence assumption on the deep future of these controls, conditioned on the sequence of controls up to the current time, plus this offset delta. I'll call this offset delta the anticipation interval. This is sort of how many controls ahead of where I am in the event sequence I'm conditioning on in the control sequence. And if I make delta really large, I can anticipate very far into the future. But the trade-off is that now, to be able to see the controls that are most relevant to predicting events at time EJ, I have to look very far back into the sequence to see where those tokens have been interleaved. Are we all good with the setup so far? I think now would be a good time for questions about setup, because I'm about to relax this assumption that n equals k, and then everything will get more complicated. Does this modeling setup make sense? Do people kind of see, do people buy the structure and the assumption that I'm making? It's just a way to set up these conditional modeling problems to kind of trade off long-term dependencies with visibility of the future in the control sequence.
Can you remind me what the two bars and the
Oh, this is conditional independent. So event EJ is conditionally independent of controls starting at UJ plus delta plus 1 to the end of the control sequence, given controls U1 to J plus delta. So you only see, if we go back to one of these examples, oops, right, when I'm predicting E1, I'm assuming that I don't need to know about U6 and further. given that I do know about U1 to U5. So I'm anticipating the future of the control sequence up to some point, but no further. And everything else I don't get to see.
So the model order is still.
The model order is just autoregressive. Yeah, left to right on sequence.
How far to the back, that's predefined.
Yes, right. Yeah, I have like, if it's a transformer, maybe I have 1,000 tokens of context. Well, okay, that's sort of silly for this example, but maybe for this example, maybe I have like a trigram model. So then when I have E1, I'm seeing U3, U4, U5. When I predict E2, I'm seeing U5, E1, and U6. When I'm predicting E3 at U6, U2, or E2, U7, etc. Yeah.
Hey, John.
Yeah.
So there are infinite ways one can set up this conditioning. I wonder if, like, if I think of music, there seems to be some notion of periodicity. And is that something that can be, you can either build it by hand or can even automatically learn that? By that I mean, maybe instead of, saying every historical position is equally important.
Yeah.
Right. So it's kind of like my current time, maybe it's like one full measures before me is more important than something intermediate.
Yeah. So I think there's interesting work going on now, more in the NLP community, on retrieval augmented generation, where you're sort of typically that's phrased as like reaching into a data set to retrieve stuff to put into your context that might be relevant for a given prediction task. But you can also think about self-retrieval problems where you're reaching into your own past to pick the things that you might want to pick, and sort of be dynamic about what you're loading into your short-term memory for making predictions. I think this is like a fascinating research direction. It is in the music domain wholly unexplored, and I think underexplored even maybe in the NLP domain, where people are more thinking about like retrieval from a corpus rather than self-retrieval on your own history. I think it's a tricky problem to get, like a tricky optimization problem to get right. But it's very interesting. You need some notion at the very least of like some kind of you need some metric or criterion for retrieving stuff, and it gets tricky. But yeah, here we're just gonna construct these sequences, and we have a strong opinion about what's relevant. What's relevant are the most recent events in the history, and then the most recent controls in the history, and future controls up to this anticipation interval in the future. And that's a sort of a very explicit inductive bias about what's going to be important for making predictions. All right, so now everything's going to get a little more complicated, because now we're not going to assume that we have sort of the same number of events and controls, and we're going to actually also assume that maybe these events and controls could be situated in time and possibly arriving like asynchronous with each other. So instead of just a regular sequence, I'm now going to have a temporal point process where every event in this sequence is a pair of scalar time, and then some mark that in the case of music will be like whatever the information is that's associated with a note. So when does this note occur in time, and then maybe like the pitch and instrument associated with this note. And I want to build a sequence model over the sequence of events. And this might look a little scary because now I have like tuples and scalars, and what do I do? But nothing's really that bad. I just sort of interleave events and serialize it. And then maybe I discretize these scalar time values into tokens that I can feed into my standard discrete autoregressive modeling toolbox. So there's nothing really that complicated yet. This is all fine.
So maybe in this, what's the assumption of the duration of the note or something, or am I mistaken?
Yeah, so I'll just roll the duration up into this mark.
Okay.
So actually, to be very explicit, this mark itself is going to be a triple of the pitch of the note, which will be a discretized value, the instrument, which is going to be one of a class of instruments, and then a duration, which will also be a quantized time value. So actually, so this mark would itself expand into, say, a tuple of values that I, again, just sort of expand out and serialize, and now I just have a sequence.
So that gives potentially, when you play a new note where the other one's still kind of fading and stuff like that, that could be that.
You'll be able to see that, because you'll see the previous notes and see what their durations were, and maybe internally in the model do some arithmetic to figure out if the note's still playing. And yeah. Right, so everything is still fine here.
Can I ask?
Yeah.
So I'm trying to understand what's the, like, what we are trying to get to. So
Yeah.
the goal is conditional music synthesis, as far as I understand, right? So this means I give you few seconds or whatever, like the time scale is not important. I give you some like seconds of signal, and then I want you to continue from that point onwards to continue synthesizing the music, right? Okay, but then here's the interesting thing. Let's say I give you 10 seconds of music.
Yeah.
And what you just presented in the previous slide was that in the first 5 seconds, I will not output anything, but after 5 seconds, I will start outputting. But what is important is the last thing I gave you as a sample, right?
So let's, so there's,
was this clear? If this was
I think let me, so there's 2 different settings. So this model, I can pretty easily just continue the sequence, right? I have an autoregressive model. So if I have the first 10 seconds, then I can just start sampling tokens following the first 10 seconds and continue. The other setting that I was talking about before is where I have now these controls. So think about controls as being like, again, this example of a melody. So I have the melody, which has notes coming in at various points in time. And these events are going to be a harmonizing accompaniment, which is also appearing at points in time, possibly, but not like lined up neatly with the melody, because I could have a note in the accompaniment that doesn't occur at the same time. I could have multiple notes in the accompaniment. And so now I need to figure out how to generate the events in this sequence, conditioned on this sequence of controls that are kind of interleaved in time with the events. And this is the challenge that I was motivating before with this sort of paired off events and controls situation. Does that make sense?
It still doesn't answer what I like. What I meant is that if like you start synthesizing after the first few samples of controls that I have provided, you might have a severe discontinuity with the last controls I provided. But in the end, like what you care is to continue from the last controls I provided, not from the first few, right? So your setting.
Let's go back to the simpler setting and look at this. So imagine like this is like a very simple, this is like a duet. So the controls, which are my melody, are paired off with there's like one accompaniment note. So E1 is supposed to be happening at the same time as U1, E2 the same time as U1. So what I'm saying here when I set up the sequence learning problem here is that when I'm predicting the first event in the sequence at time 1, I get to see the melody note that's being played at time 1 and several of these upcoming melody notes in time. I'm kind of previewing what's going to happen ahead of time in the future in the melody when I'm predicting the first note in the harmony. When I'm predicting the second note in the second note in the harmony, I get to see a little bit further into the future of the melody. So there's no there is a discontinuity in that I always, when I'm predicting a particular note in the melody, only get to see a certain number of or a certain note in the harmony. I only get to see a certain number of notes into the future in the melody, which is the conditional independence assumption that I made, that I don't need to see the whole future of the melody to figure out what comes next in the harmony. I only need to see the past of the melody plus a bit of a look ahead.
Yeah, maybe if you go back to the initial, even the before slide, maybe this one. He's not just generating given till now on future. He's actually generating things that are
right. So like if I'm wanting to generate the harmony at this time, so starting generating the red notes starting from here, I'm actually seeing the melody maybe all the way up to here. I'm always like looking ahead in the melody when I'm generating the notes in the harmony. So I see here when I'm generating the harmony here, I see the past of the harmony, the past of the melody, and the future of the melody up to this interval delta. So I have a look ahead that I've created. So I mean, another way to think about this, maybe like in sort of like older like cybernetics-y language is I have a filtering estimate based on the history of the sequence of events. I see just the history of the events, but then I also have a smoothing estimate of the sequence of controls. I see two-sided context in the controls up to some amount of time in the future.
So is it create some new channel based on the current way we already have channel? As long as you have a whole group sequence, then you create a different sequence here. I'll continuously writing the melody.
Yeah, so here I'm generating notes in this red sequence, given, and I've starting from the notes in the blue sequence.
You should
Yeah.
probably go ahead with the.
Yeah. Right. But now things get a little more complicated because now I don't have these like nicely paired off notes in the melody and the accompaniment. So now what do? How do I set up this? Like I want to do this anticipation thing, but now I have this time variable to worry about. And the first thing to note is that I could always do this sequence to sequence thing. This will work if I'm willing to accept the fact that I have to look way back deep into history to look at the controls that might be relevant. So what's the natural generalization of this anticipation idea when I have these sort of asynchronous sequences with this time variable? Well, I think the first thing that comes to mind is, well, let's just take these controls and treat them as if they were events, but delta seconds earlier, and then sort them into the event sequence at whatever time they're appearing, but delta seconds early. It seems like a natural idea. This is the first thing I tried, and it doesn't work. This is completely broken in ways that the scale can't solve. It's just fundamentally busted. Does anyone have any intuitions about why this is busted? I wonder if the title of this slide gives a hint. So what's wrong with sort ordering these sequences? So let's think about what we want to have happen when we sample from the model. So I have a partial sequence. I have a prefix up until this event, EJ plus 4. And now it's not a regressive model. I want to keep on building up the sequence. So I'm going to sample the next value in this sequence. Well, first question I have to ask is this next event in the sequence going to be EJ plus 5, whatever that value is? Or is it going to be UK plus 5, the next control, which I have in a bag waiting to be inserted by me into the sequence? And the problem is that I don't know, because whether this is EJ plus 5 or UK plus 5 depends upon the value of EJ plus 5 when that event occurs in time, because that's what the sort order means. The sort order means that UK plus 5 goes between the last event in the sequence at a time before UK plus 5 and the first event in the sequence at a time after UK plus 5. But I don't know what sequence position that is until I've generated EJ plus 5, but I can't generate EJ plus 5 until I know whether UK plus 5 goes before it or not. So I'm dead. There's nothing I can do. I can't sample. I can train a model. I can sample unconditionally from this model. If I don't want to specify the controls myself and just run this model autoregressively, I can sample from it. But if I have a bag of controls and I want to be dropping them into the sequence myself to steer the output of the model based on them, inference is intractable. There's nothing to be done. So I have sort of this goofy cartoon of myself like sitting on top of, this is my event sequence racing down the tracks. I'm sitting here with my tracks in a box and deciding whether or not it's time to drop the next track. And with sort ordered sequences, this is just, there's no way to determine. So we're models busted. So how do we fix this? Well, what we need to do is we need to put these controls at stopping times. And if you're not familiar with the technical definition of a stopping time you should think of is just a time in the sequence that can be determined based only on the left-hand side of the sequence. So the sort order positions of tokens in the sequence is not a stopping time because I need to know both what's happening on either side of the position. But there's actually just like a little diff that we can make to this that will turn our positions of controls into stopping times, and the technical definition of it looks very messy. But if you just ignore the technical definition and look at what it actually is going to do to the sequences, if I had this sequence in sort order, I take all the controls in the sequence and just shift them past one more event in the sequence. So UK and UK plus 1 in the original sequence came before EJ, and they come after EJ in this rearranged sequence. UK plus 2 came before EJ plus 1. It comes after EJ plus 1 in the adjusted sequence. And the idea is that the sort order is not a stopping time. But one position after the sort order is a stopping time, because I can see now, after I've generated EJ plus 1, oh, if UK plus 2 was supposed to be in sort order, it would have come right before me, darn. But now I've deliberately said, no, UK plus 2 should come after that. And so I know, oh, if it were in sort order, it would have come before here. Now we've seen EJ plus 1. We've seen that it would have come before EJ plus 1 in sort order, but we're not putting it in sort order. We're putting it one after. And so I'm just in time to put it into the sequence now. And so this is a sequence index that can be determined just based on prefixes. So now I've put these controls in my training data in sort order, which means when I'm running inference, I know just from the prefix of the sequence whether it's time to drop the control into the sequence, and I can play this game sitting on top of the engine and dropping the tracks onto the track just in time as my event train is rolling down the tracks to keep the train on the tracks and generate these sequences. And I have an example worked out here, but I think in the interest of time, we can just leave. If anyone is curious to figure out exactly how this works and work out math of where tokens go in sequences, you can maybe take a look at this slide later at your leisure and figure it out. The other thing that actually I didn't say that I think I'll say if people want to ponder this a little further is that stopping time is actually a sort of unfortunate word for what's going on here. I'm using stopping time because that's the word, that's the definition. But actually, the random stopping times that I'm talking about in the sequence are actually indices. So these are really stopping indices in the sequence. It's random indices where I'm putting these events and controls, not random times in the sense of like the underlying control point process. So those are the stopping times that I'm working with. They're really better called stopping indices. All right. So that said, we now have a way of constructing these controllable models where I'm able to condition on sort of parts of the music and generate other parts of the music conditioned on these parts without the parts I'm conditioning on being pushed way too far away from the parts of the sequence they're supposed to be governing when we build these models. So we have this tool now in our toolbox for creating these controllable generative models of point processes. So let's point them at some music and see what happens. So what I've got here is I've got a training data set that was actually compiled by Colin Raffel, who's now known a little better for his work in language, if you're familiar with the name, but he actually did a PhD on music information retrieval and put together this data set in 2016 of symbolic music. So if you're not familiar with music, you should think of symbolic music as being analogous to text, in contrast to performed music, which is analogous to speech. And we're working with symbolic music here, so like the text representation of music, which is discrete and symbolic. And actually, the first thing to notice about this data set is that actually this is, if you're familiar with like language data sets, this corpus looks small. 176,000 documents, or about, depending how you count, like 663 million musical events or notes, or depending how we tokenize it, maybe like 2 billion tokens. And again, familiar with like the work that OpenAI is doing, and people at the pile. You have 1 trillion token text data sets, 10 trillion token text data sets. So this is small. And this is one of the challenges of working in a domain like this, which is that we are somewhat fundamentally limited. So my claim is this is not just, oh, I haven't worked enough to collect data, or it's just like every human on the planet is a natural generator of language. And increasingly, this language is mediated by the internet, and it gets sort of logged and scooped up and scraped into these training data sets. And we get large volumes of data because people are large producers of data. A prolific composer in their lifetime will produce like 100 to 1,000 musical documents. And most people are not composers. So this is not just an artifact of difficulty collecting data. This is a fact of sort of human nature that we're fundamentally data constrained in this domain in ways that we're not for text.
So there's no way for data augmentation?
There are things you can do. So I'm actually working now with audio, to pull in the audio modality and get more data from there. Not just to augment the MIDI, but also build multimodal models. Sure, you could try to play games with with data augmentations, like the games that people play in Vision. Although I think even there, you're going to start. So in fact, like we'll see maybe at the end a little bit of training. You'll see like I'm taking 500 passes over my training data, which feels like a very familiar kind of operation for people who are used to working in the vision domain and working like with CCAR10 or ImageNet. It feels very wrong to someone who's familiar with the natural language processing methodology where everything is single pass. So you have a data set that's so large that you train your model for 100,000 steps or 1,000,000 steps, and every step sees fresh samples from the data distribution. So yeah, we really are living much more in a domain like classic sort of vision. Although now you see people in vision and see leaders in the vision community, they're working so hard to get people off of these small classic data sets because you actually can collect a lot more visual data. We now have data sets like Lion 5B with 5 billion images, and you can get more into this domain or regime that like the language folks are in with single pass training, and a lot of these regularization games that you play on small data sets are maybe not really the direction that we should be pushing on for vision when we have access to more data. But maybe we do need to be playing these games in music because maybe this is really a much more fundamental limitation in this space. Yeah, I think it's an interesting question. Yeah, so just for reference, Open Web Text, which is sort of the data set or reproduction of the data set that the GPT-2 models were trained on, was 10 billion tokens. So even back 2018 era, GPT-2 scale models were trained on much larger data sets than this. And then sort of the models that I'm working with are very much like the GPT-2 family of models are sort of one of our ambitions of this work initially was, oh, let's see if we can like replicate the GPT-2 for music with GPT-2 style models. And actually one thing to note here is that these models that I'm working with, the architecture of the models are completely standard autoregressive GPT-2 style transformer models. All of these games that I'm playing with the conditioning and anticipation happen entirely in pre-processing the data set. And I create these sequences in particular ways to get these control capabilities. But at the end of the day, I shovel them all into a completely standard autoregressive transformer off the shelf, no modifications. And we look at 3 scales of models, so borrowing from the methodology of the original GPT-2 paper. I would have trained an XL model, but we'll see that there was no need because we're data constrained, not compute. And then a couple of optimization schedules, 100,000 steps and 800,000 steps with pretty standard training methodology. So then what are these tasks that I'm setting up? So I'm going to want to train these models with anticipation to solve tasks. And the tasks that I'm going to solve are conditional infilling models. So in particular, I'm going to take sequences of musical notes in my training data and partition in them into 2 parts. One part of which will be the controls that I'm conditioning on, and one part is the events that I want the model to be able to generate. And I'll set my anticipation interval for how far ahead in the control sequence I'm going to look ahead for conditional generation. And I need to generate to define some tasks. And so in particular, I think the 2 interesting tasks to look at here are temporal infilling tasks and then instrument conditioned tasks. So the temporal infilling task is where the notes that I'm anticipating are at the end of some temporal span in time, and I'm trying to generate tokens that are consistent with some boundary at the other end of this span to fill in a missing span of music. Like I deleted a measure from the music and I want to fill in a new version of this measure. And then these instrument conditional sequences are where I have some instrumental parts and I want to generate other instrumental parts. So this is more like that melody conditioned generation that I was using as a running example, where maybe I have like a violin part and I want to fill in a piano part interleaved with this violin part. So in that case, I would be identifying the violin notes in this training example as controls, and then the piano part as the events. And we also played some games where we sort of took random notes and designated those from training examples and designated those to be controls. And I hope that maybe we should get some generalization to other kinds of infilling tasks that we hadn't really considered. We don't really evaluate this. I'm not convinced that we really succeeded that much in getting sort of general purpose control out of these, but the spans in instrument condition generation at least seem to work quite well. The other point I wanted, so you had asked about data augmentation. You could also think about this as a kind of augmentation that I'm applying to the training data, where I have sort of unconditional sequences where everything is an event, but then I have all of these different sort of random conditional generation problems that I posed to the model, where I like took a few of the parts and I designated them as control parts, and then can you generate me the rest of the parts given these control parts? Or I took some random spans, and there's some randomization happening in here that you might hope would behave as some kind of augmentation. I was actually somewhat optimistic this might behave as augmentation. We'll see in the results that maybe it didn't help that much, but it is a kind of augmentation.
What do the tokens look like in these data sets? Because like your instrumental, you mentioned that marks were triples, right? Like instruments was like classes, again, like 0, 1, 2, 3, 4, 5, or do you like have bespoke tokens for each of these things?
Yeah, so the data, the origin of all this data is this format called MIDI, which is an ancient format, and it has like 128 different sort of instrument codes. So it's a class where they're sort of pre-specified. Why 128? Well, because this format was invented in the 70s for doing data interchange over like cables, and they used 1 byte, 7 bits, and then they sort of took as many instruments as they could fit into 7 bits, and most of them kind of make sense. Like there's a a bit there's a code for cello, and a code for piano, and a code for trombone and electric guitar.
Nice.
There's also a bit for the Goblin's effect, which yes, there's some interesting artifacts of the early days of music synthesis in there. But that's where instrument codes. There's also 128 pitch codes, which are sort of assigning class labels to different like notes in the classical 12-tone Western scale. Yeah, so if you want like quarter tones, like good luck.
So your tokenizer is just like very easy, like you don't have to train anything.
That's right. There's no learning going on in tokenization. Yeah, I'm just pulling the symbolic data out of these sequences and parsing it. And sort of in a nod to my comments at the beginning of the talk, where I sort of remarked that the compute is important, I like to say a little bit about compute resources used to train these models, which I think can be, well, they're not that bad, but a little eye-raising for people who aren't familiar with the domain. So these are by modern standards quite small models we trained. So the small models were about 100 million parameters, medium is 300 million, and this large one I trained was 780 million parameters. So these are all sub-billion parameter, which these days is considered quite small by language modeling standards. We train them for either 100,000 steps or 800,000 steps, which again are pretty sort of standard training schedules. And I'm actually optimizing these, the hardware is these V3 Google TPU machines, generously provided by Google. For us, and if you're more familiar with GPUs, one of these V332 machines is approximately equivalent to 8 A100s linked together. And total training time on one of these machines, we had multiple machines and we did things in parallel, but if we did it all serially, it would have been 47 days on a machine with 8 A100s. So this is, I think, within the range of what is possible in academia, but kind of at the limits of, we can generally maybe get access to a box.
Do you do this
like
every
this.
time starting from scratch, or do you have somewhere in pre-trained model you can adapt to it?
Yeah, so here we were looking at pre-training. So we're training these models from scratch. Fine-tuning is much more lightweight. And actually, you can fine-tune these models. I fine-tune, actually, one of my to-do list items this fall is to try to get some documentation out to help people more clearly understand how to fine-tune these models. But if you have like a small data set and you want to do some fine-tuning, you can do like, well, if it's a small data set, you'll just start overfitting almost immediately anyway. So
GitHub URL somewhere.
Yeah. But within the next couple of months, also a nice documentation of how to do fine-tuning. And for fine-tuning, you need much fewer resources. So this is for training from scratch. And yeah, that's about sort of the scope of what. So yeah, you see, for like a small model, training a small model for 100,000, this is GPT-2 small scale, for 100,000 steps is actually about a day on one of these boxes, which is quite reasonable. Training at the medium or large scale model, these numbers start to get a little more difficult.
There's
contemplate.
a rule of
But
thumb that how many training data you have
yeah,
versus how large, number of parameter you have. If you have a small data set, you don't want to get a billion parameter model to start with, right?
yeah. So let's actually let me maybe actually hold that thought. I want to talk a little bit about a particular point about eval. Actually related to your earlier question before we get to, so great questions. I have slides for all of these questions. So, okay, let's answer your question now about data augmentation, or at least a part of your question about data augmentation. So one thing that you might ask is, well, I have this model now that's trained not just to do unconditional generation of sequences, but to solve all these sort of, rich and random infilling kinds of tasks. Is this going to help me in the sense that I'm data constrained and maybe this is useful data augmentation? Is it going to hurt me in the sense that I have a limited capacity model and now I'm asking it to solve many different kinds of problems and maybe I'll suffer at the unconditional modeling task? So what we're going to look at here in this massive table of numbers is log losses of the model. And the numbers that I want to draw your attention to are first this small 128 million parameter model trained for 100,000 steps, and two versions of it. One of which is trained, this flag field is trained just on unconditional generative modeling tasks. So no controls, just the pure training sequences. And the second model that's trained with this rich sort of set of infilling objectives. And if you look at the log loss of these models, they're basically sitting right on top of each other. So you could be sad and say, oh, I hope that this would be a nice data augmentation and I would get some, some win out of this and be disappointed. Or you might be extremely pleased and say, look, I have this model with all these capabilities that a standard autoregressive model doesn't have, and I got it for free without any sacrifice. And to be clear, this is log loss on unconditional sequences. So I'm just measuring performance. So what I'm seeing is I have this model that was trained on all of these auxiliary training objectives, so all these different kinds of control tasks, and it's doing just as well as the model trained on just the pure generation task. So I didn't get really an augmentation win, but I didn't lose anything either, and I think I'll call that a win. And this holds up at the larger scale and more iterations as well. But the sort of the sad thing here is that we are clearly data limited. I trained these small, medium, and large models. A glaring question here is like, well, where's the XL model? GPT-4 had 4 models that had small, medium, large, and XL. Why didn't you train XL? And the answer is that, well, I trained the large model for 100,000 steps, and there didn't seem to be any point in going further. Because if you look at this curve, training curve at the bottom of this set of curves for all these models I trained, here's train for the large model. It's doing really well, beating out all these other models on the training data, fitting well. And on test, it's barely better than medium. I'm getting extreme diminishing returns.
So overfitting shows up.
Yep, absolutely. And to think about this also, so this is 10 to the 5, 100,000 steps versus and here's the 800,000 steps models. So the training data for this is about 3,000 or 3,300 steps. So actually, I'm taking for 800,000 steps, I'm taking like 400 passes over the training data. And so it's not surprising that overfitting would start to show up. And in fact, it clearly does. And if we wanted to train larger models, we need more data, or we need clever augmentation, or we need more modalities, or we need an idea. Like we're not just going, like we're not going to solve this problem just with scale. We need an idea for how to make further progress on this problem. And then also, I think I'll refer to the paper for sort of human eval results and how well this model is doing from, say, a human perspective, especially like the log loss numbers don't mean anything to you. They probably don't mean anything to me either, except as sort of relative values between different models. But I think rather than bore you with another table of results, I'll just play some demos for you, and you can sort of repeat we can recreate the human eval experiments that we posed for people that are summarized in those tables. So actually, this example that we're going to listen to here is I'm going to rip out the melody from Dua Lipa's Levitating song from 2020. And then we're going to condition on that melody, and we're going to give a new harmonizing accompaniment of the melody using the model. Why Levitating from 2020? Well, the data set was collected in 2016. So hopefully this is not in my training data. Although I just saw earlier this year that Dua Lipa got hit for a copyright lawsuit, arguing that this isn't that. But like, this is a big challenge for music in general, and I think it's not like a data cleaning challenge. It's like a fundamental question of like, what does it mean to generalize, and what is a copy, and like what constitutes test set contamination. This is the best that I can do. So actually, first what I'm going to play for you is the original version of this song, which is not the version that you're used to hearing on the radio, because it's a synthesis of the symbolic representation of this. So just to get it in your ear and sort of what the bass line sounds like. You can, yeah. So now, again, like I'm going to do what I said I'm going to do. I'm going to rip out the melody. So now we're going to listen to just what we're conditioning on. And actually what I'm going to do is I'm going to condition on everything from the first few seconds of the piece, just to sort of get the instrumentation right, so we don't do something completely different as far as that. But then after the first 2 seconds, we're going to have just the melody. And so this is all the notes that we're conditioning on. And now we're going to fill it in with the model. There it is. And if you don't believe me, if you think it's cherry picked, we have a blog post online with all of the results from the human eval. I think we have like 100 different generations from these models and a few other demos highlighted. Play around with it and see what you think. Yeah, as I came up earlier, the code and the pre-trained models here are also available on GitHub and the paper as well on Archive. We're actually done in pretty good time, and there's time for questions. Thank you all for being here.
We can sue, but because it's similar to some of the real music.
Yeah, so these are the copyright questions. We were a little bit concerned about this when we were putting the paper together. There's actually, we wrote a 2-page ethics statement in this paper that I think, in retrospect, no one cared. But it's there, and if you care, you can go read it, and I would appreciate it. I think the pragmatic answer, which we sort of realized in retrospect, is that nobody cares about MIDI. It's like, it sounds like a video game. No one, really what it is no one feels threatened. And a lot of what goes on in copyright law is very pragmatic, right? People bring cases when they feel threatened or they feel that their commercial interests are being violated. And so, again, like OpenAI in the text domain, there haven't been a lot of lawsuits. They've been able to get away with law because there's not a lot of precedent. The music domain is extremely litigious, but only in the audio domain. And no one seems to care about MIDI. And in fact, this data set that we're training on contains all this stuff, like it's full of the Beatles and other stuff that people get sued for all the time, but it's in this MIDI format. And I don't think that, like, objectively, like intellectually, like maybe you have a case, maybe you don't have a case. Certainly seems like you have an argument that there's copyright infringement happening. In practice, Colin's had it just up on his website since 2016. No one sued him. No one seems interested in suing us. We seem to be okay. We were putting together a promotional video on this at Stanford, and they expressed, so we're not running with the Dua Lipa demo for the promotional video, but it does seem that MIDI seems okay. We're working right now on multimodal audio models that bring in the audio modality, in part because we put this model up and no one seemed to care. Again, because it's MIDI, and so we thought we'll do audio, and so maybe people will care, maybe we'll get more attention, and also maybe we'll get sued. Hopefully not. We're trying to be careful. We're thinking through the issues. If anyone wants to talk about this more offline, I'd be happy to talk for hours about the complexities of dealing with this data, and also the ethics, to be clear, I think. But I do think that the sort of the copyright law issues and the ethical questions of working with this data are somewhat divorced. Question?
So how, sorry, in your experience, how does it differ? Like, okay, you showed us one very nice demo. How does it differ across different music styles, right? Because I assume that the dataset is not uniform over different styles of music.
Yep. So I think the most convincing way to convince yourself of that is to go on the blog and just play around a little bit with these demos. So I think I wonder if I can, where's my, oh, there I am. Oh, but now this is going to be too hard. We won't do this now. The quick summary is that most of the training data is modern Western pop music. And so if you have some kind of pop, it's going to do great. It does reasonably well with classical music as long as you don't push it. So it can't do a Bach fugue. I tried to get it to generate a fugue and it just has no understanding of like the structure of the fugue and how to do this. And then anything sort of outside of sort of pop or classical Western music, you're way out of distribution and all bets are off. And that's purely just because of the nature of the training data that we're pretty constrained to this modality.
I have a couple of questions. Like one being, so when it does screw up, what are the failure cases like? Like, are they cases where it's like to some extent noise, but I guess like in MIDI you can't regenerate
no,
noise.
you don't get that. So like for the Bach fugues, for example, you might hope that it will like continue on with the fugue idea, and it just doesn't. It just starts, generating music that sounds kind of like, like poppy classical, like elevator Bach.
But does it sound good? Like, is it like stay on scale?
It sounds okay. I mean, like, yes.
So what I'm
it's not like catastrophic failure, like it. Yeah.
So it has in some sense understood like the rudiments of what sounds good, and it sort of sticks to that.
I think that's fair. And in fact, you see it in the human eval. So for these conditional generation tasks where we have like the melody and we ask it to generate the accompaniment, the human eval people actually, not statistically significantly, but marginally preferred the model's outputs to the originals. And I think that if we'd run a larger scale study, I think that statistically it would have become significant. And the reason is that the model's a little conservative. And if you're asking sort of human evaluators, depending how you prompt them, like what sounds more sort of conventionally musical, they'll pick the more conservative one, and that's more likely to be the model. And so it slightly ekes out. But yeah, it does tend to be a little bit on the conservative side, especially if you start playing with like nucleus or temperature decoding parameters.
Nice.
Yeah.
The second question I had is somebody else.
I mean, beyond just whether it sounds good, and you have musicians look at it and see whether it makes sense from a musical theory point of view. Does it do weird things in terms of arranging?
It's a good question. So I haven't done like a study with musicians. I'm a fairly I was like a classical cellist as a kid and took composition classes and the big failure case that I briefly talked about is the Bach fugues, and it's just terrible. For say like pop music, it writes very convincing pop music. It does not follow. So for other kinds of classical music, like if you prompt it with like Mozart, it will continue for a while in sort of a Mozart-y kind of structure. It will not do long form generation. So like it won't understand like if you have a Mozart piano sonata that, oh, there's supposed to be like an A, B, A kinds of structure. And that's like purely a modeling, well, not purely, but in large part modeling constraint that you have like 1,000 token transformer and it literally can't see. We do have some work that we've done, preliminary experiments, fine-tuning for long context. And there the situation gets more subtle, but the sort of the first order observation is that you still don't get the long-term structure. You sample, but the reason is not because the model isn't picking up on it. It's just that the model at these like 100 million, 300 million parameter scales isn't good enough to maintain coherent generation over those long-term structures. So like we really, I think, need to be getting more to billion parameter models and finding the data to feed those models to be able to produce those structures.
We'll probably like take one last question and then wrap up, and then if others I think we'll need to kind of wrap up and one more question.
I don't get how the model can like model the stopping times that well, because like each token be like very long sustained note, or it could be like a super short note. Does a model show like a preference towards shorter notes or longer notes, or like?
So the durations of notes are really just part of the mark in this temporal point process. So it's sort of like metadata. What's really sort of important from the stopping times and temporal point process modeling perspective is onset times and how the onset times relate to each other. So the stopping times have to do entirely with onsets. So yeah. So if you like sort ordered the controls, it would be like between which two events onset times does it go, and then with the modified stopping time order, it's like one onset, after the event, yeah, with the onset where it would have appeared in sort order. Yeah, but the durations are sort of irrelevant from that perspective. They're just some extra metadata tacked on to the prediction.
Okay.
So let's thank John for the excellent.
That's not the time.
Thank you, everyone.